welcome to the deep dive. Today, we're getting into something pretty mind-bending called motion theory.
Yeah, it's a really different way of looking at things. Forget particles, forget forces as the sort of bedrock.
Instead, picture this. The universe as structured motion. Everything is rhythm, patterns moving. The question isn't, what is it anymore?
Exactly. It becomes what's moving and, what's the motion actually doing? It's a huge shift.
And that leads us to this fascinating idea we're exploring today, the telescope confession.
Sounds intriguing.
Right. The idea is, could our telescopes, these amazing tools we built to see light from stars, galaxies, could they have been accidentally proving motion theory all along?
Without us quite realizing it, you mean?
Yeah. Because the standard view is pretty simple, right? Telescopes collect photons, light travels for ages, hits the mirror.
And we see the past. Light buckets, essentially.
Light buckets, exactly.
Yeah.
But what if that's not the whole story? What if they're more like rhythm resolvers?
Okay, rhythm resolvers, meaning?
Meaning, the clearer images we get from better telescopes aren't just down to catching more photons, but maybe getting into better sync with some underlying cosmic motion.
Interesting. So better sync, not just better light collection.
That's the proposition.
Yeah.
So for this deep dive, we want to look at how telescopes evolved. Keck, Hubble, JWST.
And see if those technological leaps, maybe unintentionally, line up with these motion theory ideas. Coherence, synchronization, that sort of thing.
Let's start with a classic problem. Blurry stars. You look through an early telescope and stars kind of shimmer and wobble, don't they? Why was that?
Yeah. That's mostly the Earth's atmosphere. It's like looking through shimmering water on a hot day.
Okay, so the air messes with the light.
Precisely. Air isn't perfectly uniform. It has different temperatures, densities. It's always moving. Turbulence. This distorts the incoming wavefronts of light.
Wavefronts, like the structured pattern of the light.
Exactly. The atmosphere scrambles that pattern, makes it arrive unevenly, hence the wobble and blur.
So fixing that wasn't just about building a bigger light bucket, was it? Because a bigger blurry image isn't the goal. That's where adaptive optics comes in, right?
Correct. Adaptive optics was a game changer.
How does it work? And why is it so, suggestive if you're thinking about motion theory? Because it's actively doing something to the light, not just passively collecting it.
Right. And what it's doing is key. It doesn't add more photons. What it does is measure the atmospheric distortion, like millisecond by millisecond.
Okay.
And then it uses tiny actuators to bend the telescope's secondary mirror, or sometimes the main one, in exactly the opposite way.
To cancel out the atmospheric wobble.
Precisely. It's like noise cancellation for light waves.
Oh.
It actively corrects the shape of the incoming wavefront.
So it's not adding light. It's, like the source says, realigning the rhythm, correcting the phase mismatch. What does that mean in this motion context?
Okay, think of it like this. If light is structured motion, the atmosphere is knocking that structure out of whack. Different parts arrive slightly out of step. That's the phase mismatch. Adaptive optics pushes them back into step. It restores the coherence of that motion pattern.
So clarity isn't just about having enough light.
No, it's about the coherence of the light, the synchronization of its underlying structure. Vision fails when coherence breaks down, not just when light dims.
Like an orchestra playing out of time.
Perfect analogy. Adaptive optics is the conductor bringing everyone back to the same beat. We're restoring the fidelity of the structured motion.
Okay, that makes sense. So we weren't just cleaning up photon paths, we were fixing the motion pattern. Now, let's jump to space. The James Webb Space Telescope.
JWST.
It's way up there, no atmosphere. So problem solved. No need for adaptive optics anymore.
You'd think so, wouldn't you? But JWST has its own, arguably even more intense system called wavefront sensing and control.
Why? What's it controlling if there's no atmosphere?
Well, remember, JWST's main mirror isn't one solid piece like Hubble's. It's made of 18 separate hexagonal segments.
Right, the honeycomb look.
Exactly. And for the telescope to work as one perfect mirror, those 18 segments have to be aligned with mind-boggling precision. We're talking nanometers.
Nanometers, that's incredibly small. Why? If they're slightly off, wouldn't it just be like a slightly smaller mirror, catching a bit less light? Why does the alignment have to be so perfect in empty space?
This is where it gets really interesting for motion theory. The thinking is, JWST's power isn't just its size or location. It's this ability to maintain almost perfect phase coherence, perfect sync across all segments.
Sync with what?
Sync with the incoming structured motion patterns it's observing. If those segments are even a tiny bit misaligned, the coherence is lost. The rhythm gets scrambled.
And you get a blurry image, even without atmosphere.
Exactly. The blur isn't from the journey, it's from the telescope itself failing to maintain sync with the structure of the light.
So when the source says JWST is locking onto still active rhythmic motion, it means it's not just seeing old photons, but tuning into a pattern that's still, in some sense, live.
That's the implication, yes. It suggests that the structure, the rhythm, persists. And JWST's incredible stability and segment control allow it to maintain sync with that structure far better than previous telescopes could.
Which explains why it sees galaxies Hubble saw, but way clearer.
Precisely. It's not that the galaxies suddenly changed. The rhythmic patterns were likely always there. JWST is just much, much better at resolving them because it stays perfectly synchronized. We're achieving better coherence.
Okay, so let's trace this. Hubble. Then ground-based scopes with adaptive optics like Keck. Now JWST with its segment control. The argument is each step was less about grabbing more light overall and more about improving phase resolution.
That's the core argument, yes. Improving the ability to resolve the fine details of the structure of the light, its phase, its rhythm.
Which reframes telescopes completely, not passive light buckets.
But active rhythm stabilizers or motion alignment machines, they're working to maintain the coherence of the signal.
And if you think about it that way, some old questions seem different. Like, why do we need real-time mirror adjustments if the photons have already finished their trip?
Right. If the information is just stamped onto individual particles, why should a wobbly mirror at the end blur the image? The photon's already here.
And why the obsession with nanometer alignment for JWST if it's just about detecting particles? Surely just pointing vaguely counts.
These are the points that challenge the simple photon picture. The fact that alignment and real-time correction are so critical suggests the wave nature, the structured motion, the phase relationships across the wavefront are paramount.
It implies the information isn't just in the photons, but in their collective synchronized structure.
That's the idea. The relationship between the parts of the wave matters. Lose that relationship, lose the coherence.
And you get blur, so blurriness is lost rhythm.
In clarity is reestablished motion coherence. It's a fundamental shift in what seeing means.
Which brings us neatly to the telescope confession. What's the confession? What are the telescopes admitting?
The confession, essentially, is that telescopes are fundamentally built to resolve motion and detect structure, not just see light and detect history.
Right.
Every time we improve them, better mirrors, adaptive optics, phase control, like on JWST, we were perhaps unknowingly building machines better equipped to deal with light as live, structured motion within some kind of cosmic medium or substrate.
We thought we were building better photon collectors.
But we were actually building better motion synchronizers. That's the confession.
And the big implication, but this is right, when we look at a galaxy billions of light years away,
we might not be seeing a static snapshot from the past, carried by ancient photons alone.
Instead,
we might be synchronizing with a structured motion pattern that still exists, still active, still unfolding across the cosmos. We're tuning into something happening, in a sense, now, albeit a pattern originating far away and long ago.
Wow. Okay. That does rewrite things. We're not passive history viewers.
We're active participants syncing up with ongoing cosmic dynamics.
So it's kind of ironic. Our drive for just clearer pictures unintentionally pushed us to build machines that seem to confirm this radical idea about motion being fundamental.
It seems that way. We aimed for better light capture and ended up building incredibly sophisticated motion coherence devices. The engineering solutions seem to point towards motion theory principles.
From passive observers to active synchronizers, tuning into cosmic rhythms.
That's the shift in perspective, yeah.
So this telescope confession, it really forces you to think, doesn't it? If our main tools for probing the universe are fundamentally about motion and sync, what else works that way?
Could it apply to other senses, to how matter itself is structured?
Yeah.
Does it change how we think about quantum mechanics, even?
What other scientific ideas might need a rethink through this lens? It feels like it opens up a whole new set of questions about reality itself.
Absolutely. It suggests maybe some of our most basic ideas about light, space, and time aren't the full picture. It's definitely provocative.
A lot to chew on there. It feels like we might be just scratching the surface.
Could be. The universe still has plenty of secrets. And maybe looking at it through the lens of motion unlocks the next layer.